Okay, so this is week 8 of Control and Instrumentation from North Island College. We were supposed to be going on to Instrumentation this week, but because we were a week behind, I'm going to do the last little bit of Control, which is the bit on block diagrams. This is quite an important bit. You need to be able to do this stuff. Okay, it's very common exam questions. It might be more than one exam question, in fact. It's actually pretty easy, I think, but I know what I think is easy is not necessarily easy for students. There's a good bit of algebra in it, so you just need to pay attention. Quite a short lecture. It's one of these things you really have to do it, rather than just watch me doing it, so I guess if you do the self-assessment questions for this week, that would probably help. And what it is, it's actually going to be week 4's material, okay? So it's kind of the week that we missed, because I skipped ahead to cover you some of your stuff for your coursework. Okay, can you see okay from there?
Yeah, better.
Okay. Right, I'll just switch over to the PC view then. So like I was saying, just to make it really clear, so the week 4 stuff, so control, week 4 block diagram models. And it's from chapter 5 of the core book in the East. So I'll turn the lights down. See that? I have to say the example I'm going to go over in the PowerPoint is a wee bit more difficult than the sort of examples you'll probably have to do. So don't panic if you can't do it, but you do have to understand the principles. Okay, so I'll just go through the PowerPoint because I haven't really had much time to prepare. I was off yesterday. That's fine, really. Oh, the other thing I was saying, for the people who are remote, I've marked all your coursework, so they'll all be first marked. And I'll release the first marks today so you can see them. Huh? But I was telling the guys here that they could still change because they've not been second marked, and they can change at the exam board as well. The external examiner can decide that they're not right marks or whatever. I don't know. They don't very often do that, but they are entitled to do that. So right, let's go from there. Everybody okay today?
Magic.
Yeah.
Sure.
Looking forward to it. You all did quite a good job on your coursework, so that's quite impressive. Yeah. Hopefully we're working on the next one. So we're talking about block diagram models. We've done a little bit of this already because I've already showed you what happens if you have a feedback block in your like a sensor transfer function and how that translates to a total transfer function.
Robert, come on, lad.
You're alright, we've just done. Everybody here today? Okay, so there's some rules to moving the blocks around in your model. As I say, you've already seen a couple of them. You've seen how to convert a closed loop model to an equivalent open loop model just by G of S over 1 plus G of S times H of S. You've done that already. Can't remember where, but I've certainly covered that with you. But there's some sort of main elements to a block diagram, which you've mostly seen already. You've got your reference input, which is always R. These are in the Laplace domain, obviously, as well. That's why you've got bracket sets here. You've got control output, so that's your main signals. You've got signals that do flow through the diagram as well, like E of brackets S normally stands for the error that comes out of the error. If it's an error detector, that one's not. That one's actually a summing point. But if it's an error detector, you'd have an E of S here. You've seen your transfer function G of S many times. That's just a standard. I don't know why they call it G, but that's just the standard that they use. So, and then the feedback one's normally H, as you know as well. So you can get things like summing points, which can also be used as error detectors as well. And obviously what you get out of that is just the sum of the 3 inputs. So in this case, these two are positive and that one's negative. So you can quite clearly see, I think it's quite easy, that that's going to be that one plus that one minus that one. Straightforward, yeah. Nobody got any problem with that, I'm hoping. You can have pick-off points, so that's like the point where your feedback comes from. And the signal at the pick-off point is the same as the signal going into the pick-off point, which you can see there. Then you can have cascaded controllers, which is what we covered in the lecture about your coursework B, because what you're designing there is cascaded controllers, a P controller, an I controller, and a D controller. Or you can also have cascaded transfer functions. It's equivalent, same thing really. So they just multiply together, and you already know that, to give you a total here. So that looks quite easy. It's maybe not quite so easy once you have the actual transfer functions. Actually, we'll just do a wee bit of maths with you, because I know people seem to struggle with algebra, which is weird when you're doing an engineering course, but there you go. I know that it's true. So just a wee bit of revision on maths. I'm just making this up. Let's make this quite easy then. I don't want to make it too difficult for you. Okay, for the few minutes, you try and work that out for me, just with a pen and a bit of paper, if you've got a pen and a bit of paper with you. If you haven't, you just have to. You guys come with no pens or paper. You do everything on the computers, all right. Well, as long as you can follow what's going on.
First thing that's happened also.
Do you want to borrow a pen? No enthusiasm there at all.
Yeah.
I'm sure there's some paper.
I've got a pencil here. To be honest.
The way you got into it.
I would tell you off, but there's really no point when you get to this level and you don't bother bringing pens and paper. The kind of thing I tell you is going to make any difference, does it?
You've gone too far.
Okay. Too far, didn't sort it out. There you go. If you want.
Cheers. So as much as
You're going to have to get quicker at this, because you're going to have to do this with an exam.
I would think it was Jack.
I guess it's a bit early.
Do you think I'll sleep?
Okay. A few more minutes. Yeah. Can I carry on?
No, we get a sense lost.
Okay.
There.
Yeah, no problem.
It's definitely going to be wrong, but they're there.
That's all right. Yeah, I think this is really easy, but I knew that students always find things easy that I think are
It's
really
easy when you
easy.
don't find everything easy though.
I know. No, I don't find everything easy. Definitely don't. I was listening into Pete's lecture on statics and dynamics. I think it was only year one, and the stuff he was talking about was like, oh, goodness, I couldn't do that subject. You'll be doing that, eh?
That's easy stuff, that's mechanical.
I think it's terrible.
Mechanical's a tier below electrical stuff.
Crack on that.
Right, yeah, if you just multiply the top line and multiply the bottom line, that's the way it works, okay? There's no cross multiplying or anything complicated. Top line times top line will give you s squared plus 4s plus 3. Bottom line is going to give you s to the 4 plus 2s cubed plus 3s squared. As easy as that, yeah? Anyone get that right? Yeah.
I did it in my head, but
You did it in your head?
I did.
Really? Okay, well, maybe you did. Okay, so that's just, actually, we'll try something else. Yeah, just a wee bit more algebra. Let's try a different page. I'm just making these up, and they don't actually represent anything in particular. Okay, simplify that. So by simplify, I mean get rid of this bit on the bottom here in particular. Yeah? That's the main thing. That denominator, this one. So this is something you have to be able to do quite quickly, definitely.
Yeah.
I think it's the bottom part, which is 25 plus 1 times the top line. I think it was like, I thought it was like to get rid of the denominator of the second, the denominator, multiply the denominator to denominator.
I understood it, but yeah.
That's what you would do now.
We'll do that. Alright, isn't it? It's good. What's that one? I'm sorry.
All these years of maths, I bet you never realised you were going to have to use them.
What did you do?
That's one is 2, 3, 8, 2, S squared still. Plus 1. 2. 2 is
Okay, yeah. Right, so there's a quite easy way of doing this. If you just follow the method every time, you'll not get these wrong, which will be good. So the easiest way, or the way I would do it, is multiply everything by that to get rid of that denominator, okay? Because this is the bit that looks pretty awful, yeah? So if you multiply everything by that, you can multiply that equation by that, it'll obviously disappear, because you'll have 2s plus 1 divided by 2s plus 1, which becomes 1, which goes here. You have to multiply this part as well, and you have to multiply the top. Is that what people did? Yeah, good. Okay, great. So we end up with, work out the answer. You can tell me if it's wrong. Becomes 2s plus 1, and at the bottom, 2s plus 1 plus s squared plus 4s. And then obviously you can simplify that a bit as well.
Top line says the same, the bottom line is 2s plus 4s plus 1.
Well, you could multiply out the top line, or you can leave it. Yeah, okay. Just say leave that. And the bottom line, you can combine the s terms. So it becomes s squared plus, what did you say, 6s plus 1?
No, 4s plus 1, I got.
You never times
it by 1, but by 8.
Have I done something wrong?
No, I think, because we got the same as that, but you never times
Right,
it
so
by
you've got a 4s term here and a 2s term here. So you can combine that. Let's multiply it out then. 6s squared. So, sorry, yeah, s squared plus
I've got s squared plus 4s plus 1.
That's not right.
1.
No, it's like it's before it. Say when you times everyone by 2s plus 1.
Times that 1, right?
Yeah, you have to multiply this 1 by that as well. That's where students often go wrong. Okay, so both sides of the plus side need to be multiplied by that. And that's all I've done there. You know, that's 2s plus 1 times 1, essentially. That made more sense. And then this was the bit that was already there. Okay? You get the method anyway. You can have a go at trying to do some more. And you can multiply out the top line. I was just going to work out what that was. 6x squared plus 3. Oh, it's too complicated. Do it separately. 3s plus 5s. Is that right? Plus 5s plus 3. I think that's right. I'm not sure. But that's easy. You can do that in 10. Okay. That's quite a common thing you have to do, because you can imagine when you've got your G transfer function, and your feedback h1, your bottom line becomes 1 plus g times h. So you end up often with equations with denominators like that on the bottom line. Okay, let's go back to the block diagrams. Any questions about that? No? Okay, I wouldn't necessarily copy it. That top line might be wrong. Somebody can tell me if that's wrong.
I think that's wrong.
Is it okay?
9-ish wrong. I think it's 9-ish.
This will be 9-ish, should it? How do you get 9?
3 times 2ish, 6ish.
Oh, you're right, yeah, that should be 9. Yeah, good, well done. Okay, that's correct, that. I should have multiplied it for yesterday. Oh, okay, come on. I'll do just now. I'll recalibrate the board if I need it again. I don't think you'll need it for a while. I know. You try writing an alarm card. It's not easy. I don't know why they drift like that.
It's got rid.
Yeah, but why has it changed since when I came in? Is it temperature? Is it time, age? These are all things that are important to your instrumentation side of the
Sounds like a good project.
Each.
Just random, I don't know. Okay, so that's straightforward anyway. These are ones, if you're looking at putting an input multiplied by some transfer functions in parallel, which you might get, for instance, PID control. You could have, you did a cascade one, but you could have parallel PID, that's quite common as well. So the idea is you would multiply each RS by each of the transfer functions and then add or subtract them as necessary with your summing block. Again, I think that's quite straightforward. You could write it like that, or you could write it as G1 times R plus G2 times R plus G3 times R. Same thing. What's the next one? Not very sure what the next one's actually showing you. Oh, that next one's just showing you the effect of doing that. And the equivalent transfer function you would get from that. Straightforward, I think. Okay, then there's an example, or a more complex example here. I don't know if you can see that very clearly. So this is fairly typical. You might have an input that could be a physical quantity. So you've got to have some kind of transducer to convert that to an electrical quantity before you put it into your controller. And then you've got your controller, like your PID part. You've got your system, like your Bitronic rig. And then you've got some feedback. You might have a transducer that's looking, again, at a physical quantity and giving you an output, and then you might need some additional signal conditioning, like maybe an amplifier or a linearization circuit. We'll cover them in more detail in the instrumentation part. But, you know, some sort of additional sensor conditioning, and then feedback into your controller, essentially, because the error detector and the controller are usually part of the same system. You probably know that from looking at things like thermostats in your house. So this is a fairly typical system, and of course you can combine it to make it a much more simple system, like this here, just by multiplying these two, to give you an equivalent here and equivalent here, and then you already know that the feedback is G over 1 plus GH. Told you that before. We worked that out from looking at the errors and the feedback. I think we did that last week. All right, okay, so they haven't actually done that one. They've just showed you what you're supposed to get. But anyway, here we go. There's more examples later on. Sometimes you might need to move the blocks around to make the combining them easier in some ways or others. So there's different ways of moving them. If you have a transfer function here and you want to move it over to this side, you also have to multiply that one by it as well. Because you can see quite clearly that that will multiply both that and that. So to move one from the from the right-hand side to the left-hand side, you move it to both inputs to your summing block. And then if you're doing the other way around, if you're moving one from the left to the right, like they've done here, it just moves across to that point, but you have to divide the feedback point with the same transfer function. Because obviously it's just multiplying the R part, it's not multiplying the X part. So if you moved it here, you're going to have to get rid of it on the X part. Okay. These are just little rules that you just need to know. They're not really, you just need to remember them. Okay, and that's just an expansion of the same idea. You know, this one's being moved over here, so we need to divide these two so that only that one's being multiplied. And this one's being moved from left to right, so you just multiply each one. Again, just little rules. You'll see it more clearly if you do an example. That one we've seen before. I thought it was quite an easy lecture today. Okay, so this one is applying, I think this is probably more likely what you've already done, which is applying with G over 1 plus GH when you have unity feedback like this. Yeah, so there's a little trick to that where you don't actually have to do the full G over 1 plus GH. You can just take this number and add it to this number, and that appears on the bottom line there. And that always works with a unity feedback. It's just the same as putting G over 1 plus GH, where the H is 1. Okay, so that's a quick way of doing that. I'm thinking there might be something we didn't do. Did I show you how to always use these unity feedback things when we're doing steady state errors? Did I talk to you about that? I can't actually remember. Okay, we can go over it in the... we'll have one revision session before the exam anyway, so we can go over it there. But when you're doing your steady state errors, you always have to put your system into this equivalent system with a unity feedback. And then your analysis, you know, of your proportional gain, your position constant, velocity constant, and acceleration constant is done on this system. But it has to have unity feedback. You can't do it on that system if there's a transfer function here. I can't remember if I told you that or not. Anyway, we'll go over it in revision. Right, so there's maybe a typical system. I don't know. You've got input, maybe some transducer to convert that to electrical, and then here we've got 3 different sensors feeding back, maybe from different points, going into a controller, maybe a controller, and that would be a system. So this one's quite an easy one. You can combine these two just by doing G2 times G3. And these one will just combine depending on what's happening here. So we've got a minus, a plus, and a minus. You can see on the next page. Oh, that's not very big. Why is that so small? Can you see that okay? I don't know. Maybe a bit small. These two, that's just the 2 forward transfer functions combined. These ones in the forward path are called forward transfer functions. And these ones in the feedback path are called feedback transfer functions. And here on the bottom we've got the H1 minus H2 plus H3. You might think that's the wrong way round, because that's a minus, that's a plus, and that's a minus. But if you look here, you can see there's a minus here. So that's why that's kind of the signs seem the wrong way around, yeah? Does that make sense? And then, of course, it's a little bit more complicated to try and make it into an equivalent open loop system like this. But that's what you end up getting. That's just doing G over 1 plus GH. You've got G on the top line, including this one, of course. But the GH part's just the bottom part. In fact, you could leave that bit out. Probably, I wonder if I can write on that. The easiest thing to do is leave anything to the left-hand side out of the equation at the beginning. So just do this bit first. Just let me write. Sometimes it does, sometimes it doesn't. So we've got G will be G3. I can't write that. I hope that's really obvious. It's not too difficult, really. That's just your G over 1 plus GH. And then this multiplies everything. So that goes on the top line. That's like a numerator multiplier, yeah? So then you just have G1 times everything else. That's kind of obvious. So if you ever see this in an exam or whatever, you know, just leave this bit right to the last, and then that just multiplies the transfer function. That's an easier way of doing it. Is that all right? Follow that okay? Yeah. So I said you won't always get examples as difficult as these. These ones you might get. It's just the very last one I was talking about. That's not particularly difficult. So they're quite time consuming to do. That's the only other thing. So actually, you might get something. I don't think you get anything as difficult as this. But if you did, there's an example here just to show you how to do this. So those two you can combine straight away. Just as 1 plus GH. I'm sorry, G over 1 plus GH. This one's probably easiest if you remove it from there and put it up there as a 1 over G2. That one just can stay as it is. The next thing you would do would be combine those. We'll see it on the next slide anyway. Maybe make more sense. There's this example is actually from the book, so you can have a look at the book yourselves. You can see down here, copyright John Wiley and Sons. That means it's from the book. So that was the G over 1 plus GH. This was the 1 over G2 I said to take out. Then you're left with this here. The G1. Oh, they've moved the G1 over because it's positive going in here. So that's just like those two are in series essentially, which we've got there. Because that's been moved over, we have to divide this one. So that's where that comes from. And then that last H1 is just the one that was there anyway. And this became a summing block. So we've got 1 over G2 going into the summing block plus G2, which just becomes a 1. It's quite complicated. I don't think you'll need to do anything as difficult as this. But anyway, so that's the first step. And then the next step would be to combine these ones together with your G over 1 plus GH formula. And the final answer looks something like that. You can have a look at this yourselves, yeah. It's quite difficult though. It's just an example to show you all the different methods. You honestly won't get anything as difficult as this, so I wouldn't worry too much about it. The other thing is it's also quite easy when you've just got G's and H's. It's a wee bit more difficult when you've got the actual transfer functions. You know, like the S over S plus 1 or S squared over 2S. That makes it a lot more difficult. This would be impossible. You wouldn't be able to do this in an exam. And it would take you too long a time to do something as complicated. Okay, then we've got some stuff. This is kind of a different subject, but you've already done this stuff, actually. This is about damping ratios, and yeah, you've done this already, so I'll skip through this quite quickly, just in case there's anything there. I don't want to miss anything, but you already know this formula. You already know how to get zeta. There's a bit of revision, omega n. So you normally would start by getting omega n, then you can work out k, then you can work out zeta. You've already done this. Some of you actually in your coursework even had complex poles, if I remember rightly. So the people who chose second order functions, I think, ended up with complex poles. So you already know about that as well. That's just with using a value k, but you've done this before. That's just using your quadratic formula. Nothing new about that. Quite a common exam question, find peak time, overshoot and settling time for a system. So first thing you need to do is make that into a closed loop system by doing G over 1 plus GH, which is here, G over 1 plus GH, I think. Is that right? Is the H just 1? Yeah, the H is just 1, so that's fine. That gives you that, then you get that, and you'll end up just doing your omega n squared equals that, 2 zeta omega n is that. Any big questions about that? You'll understand what I'm talking about here. Yeah. Quite easy. And again, you can do things like find peak time, percentage overshoot, and settling time. These are all just equations that come straight out of the book. If you need to use them in an exam, you will be given them. These particular equations. You wouldn't be expected to remember them. That one, yes. This one you need to remember, but not the others. Okay, so I don't want to scare you about the exam, but anyway, there you go. Yeah, that's about it, really. Anything else I would like to tell you about that? I think. Yeah, this is sometimes referred to as an open loop transfer function because it's like the equivalent open loop transfer function of the combined G and H transfer functions. So just be aware of that in the book. Sometimes when you're going through it, it talks about open loop transfer functions or equivalent open loop transfer functions, but that's referring to this T bracket set. Okay, and there's another example, find the value of K for a 10% overshoot. So this is a little bit similar to what you're doing in coursework 2, except you're using MATLAB to do that. So the way you would do it is, first of all, work out what was the zeta value using that equation that you've seen. This is just it rearranged. Actually, I wonder if... Just to quickly advise you how to rearrange these, I don't know how much you've done of this kind of maths. You would divide those two terms to get 0.1. That's where that 0.1 comes from. So then you get e to the power of that. Ah, sorry, this was the original formula, wasn't it? Whichever. If you've got an e to the term, you can take the log of both sides to get rid of the e term. If you've got a log on both sides, you can take e to the power of that log to get rid of the log. Yeah, so that's just a wee trick in maths. Switch back over. Not sure how much people actually understand that. I think that's right. Or log. Okay, so you can always get rid of logs and e to the powers by either taking logs or taking e to the powers. They're like the inverse of each other. Yeah? That's all that's been done there. You've seen that before in maths? Yeah, that's fine. Yeah, of course you did maths 2. Was it maths 2 this was in? I think it might have been, yeah. Most people have done that. Anybody remote who hasn't done that, you can have a look at the Int Math site or the Stroud book. Want a bit more information on that. Okay, so that's all that's done. It's just rearranged the equation from the book that you've seen already, and then just put the numbers in, really, to get zeta. You can have a look at going through that yourself, just to make sure you can rearrange something like that yourself. Again, it's just really algebra, I think. Take the logs of both sides, gets rid of that, so then you're left with this. So then... that must have come out as 2.3. And then they've taken the pi across, the negative pi across to this side. So that must have come out as minus 2.3. Of course it would be negative, because logs of decimal fractions always come out as negative. You're just left with that on that side. Then, what have they done next?
They solved the 2.3
They took this over to the other side, yeah. Just so solved that, yeah. Took that over to that side, which gave you that. Yeah. There's a bit more steps than you maybe need to do. Take the square of everything, gives you that. So the square of that and the square of that gives you the square of that, and then you can just rearrange that, yeah. Because these are common terms. Yeah. It's quite difficult algebra, but hopefully you can do that. Yeah. Try that yourselves. And I think that's just rearranging. You know that omega n is the square root of k, 2 zeta omega is that, so that's putting that in instead of the omega n part, rearranging, and eventually get value for k. What was the reason for getting? Oh, it was to give a specific value of overshoot. Yeah, which you've been doing with your coursework B anyway, but using MATLAB to do. Okay, that's the end. That was nice and easy. Right. So has anybody got any questions about anything? This is really the end of the control theory part. So from next week we'll be doing instrumentation, which I think you'll probably mostly find easier. You may find it a little bit more harder. Anybody got any questions about any of the control stuff so far? No? You've got any questions about the coursework B? Okay. Or I can do that individually with you then, maybe.
Aye.
Anything you want to ask me? No? Smell happy? Yeah? Okay, good. Right, well, you can just work on your coursework. There'll also be some self-assessment questions for this week's lecture as well. So it's week 5. Okay, remember this was week 5 that we were covering, not week 4.
Is our results ready for the
I'll do it just now. Yeah.
This call has been disconnected. Thank you for joining.